this is just another sorting algorithm. So the idea actually comes out of merge sort. So in merge sort, the main idea was that I want to sort an array. I chop it down into two parts. I sort each part separately, and then I do a merge, right? So I had this huge array. And let's say I just cut it down in two parts, the left part and the right part, and then I would sort each of them separately. But then at the end, I also had a merge step. I had to merge the left part and the right part. Now, the question that we ask for quicksort is, what if I don't want to merge? Can I do it so that I'm already sure that everything in the left side is less than or equal to everything on the right side? Because if I somehow know that, then I don't need to do merging. I know that everything on the left comes before everything on the right. Okay. So how can I take an array and cut it in half so that all the elements in the first half are smaller than the elements in the second half? Well, one way to do that is to just pick any element of the array and then just go over the whole array and look at all the elements that are smaller than the element you picked, put them on the left, look at all the elements that are larger than the element you picked, and put them on the right. Then all of the elements on your right would be larger than all the elements on the left. This is the basic idea behind quicksort. So quicksort is actually one of the easiest algorithms ever. Let's say I want to do quicksort, and I have some array A with n elements. All I do is that I first pick some elements. Let's call that element X. I pick some element X of A. And then I just create two different arrays. Let's say my left array is all of the elements Y in A that are smaller than X. And again, I'm assuming I don't have repeated elements. I'm assuming I can compare any two elements, and one of them is definitely smaller than the other one. But this is a small assumption. In practice, you can do it without this assumption as well. And then I say my right subarray is going to consist of all the elements that are bigger than X, right? So if this is the case, then I can just recursively call quicksort on the left side and on the right side, and then I don't need to merge. I can just append them. So I can just say return the result of doing quicksort on the left side. Let me not give it the size of the array. And then to the end of it, add the result of quicksort on the right side. Now, what is my base case? Again, I should never forget the base cases. The base case is if my array is really small. If my array is small, I can just avoid cutting it in two. So if my array has only one element, I say just return the same array. Or generally, you can also say if my array has less than some constant number of elements, as long as you choose a small constant. Let's say if my array has less than 100 elements, I would just use one of the sorting algorithms that I've seen before. Because it doesn't matter. If you have a small array, you can sort it in whatever way you want, and it's going to take constant time anyway. But here, I'm just going to say that for my base case, it's going to be if the size of the array is just 1, then return the array itself. Okay. Now, great. So I have a sorting algorithm that can just call itself recursively, and I don't need to merge. But now this image is a bit problematic because my left side and the right side are not going to be the same size anymore. Right, so it really depends on how I pick this X. Actually, I'm going to call this X my pivot. So if I call this, oh, this is a bad color. I will not use this color ever again. So if I call X my pivot, I'm choosing an element as the pivot, and then I'm looking at all the elements that are smaller than it and all the elements that are larger. But what can go wrong? Well, maybe my pivot is not really cutting my array into equal halves. Maybe my pivot in the worst case is just my smallest element. If my pivot is my smallest element, my left array would just be empty, and my right array would be everything. Actually, in my base case, I have to say if the size is less than or equal to 1. But I have an equally bad case where my pivot is the last element, the biggest element. In that case, everything would be in the left array and nothing on the right array. So how do I pick a pivot? Now, in practice, I can just say I pick the first element. It's as good as any other element. And I just use that. So if I want to do this, what is the worst case runtime that I can get? So you see, I'm just saying this in a hand-wavy way. I haven't proven that this is the worst case, but let's say that we agree that the worst case is when the pivot is always giving us the worst possible distribution between the left and the right. So everything always goes to the right, let's say. So in that case, if I use T of n to show my runtime on an array of size n, I'm picking this element. And then in order to create the left array and the right array, I have to go over my entire array once, just to see which elements are smaller than my pivot and which ones are larger. So that's already O(n) time. Or if I just want to count the number of comparisons that I'm doing, instead of the runtime, let's just do the comparisons. I'm doing n-1 comparisons, right? But then after that, my worst case is that I have to do T of 0, basically, because on one side I have 0. And then I have to do T of n-1 on the other side. Okay. Now, I haven't still proven that this is the worst case. I'm just saying this is one bad case, right? But if this bad case happens, and if it keeps happening, so if every time that I pick the pivot, I just pick the smallest element, I'm really unlucky, then I have this recurrence. But I can just open this recurrence, right? So T of n is just n-1, T of 0, let's say, is 0. And then T of n-1, I can open that up. It gives me n-2 plus so on, n-3, all the way to 1. And we've already seen that this is in theta of n squared. So I have at least one bad case where my runtime is n squared. Now, how can I prove that this is the case no matter what? Well, in general, if when I pick this pivot, it happens to give me a left-hand side which is of size I will get something like this. I will get T of n is n-1 plus T of I plus T of n-1 minus I. So if I have I elements on the left, I have X itself in the middle, and then I have n-1 minus I on the right. Now, you can try this with any value of I, and you can just do an induction and show that in the worst case, it would be n squared. So this is really our worst case, at least asymptotically. But of course, we don't like an n squared algorithm. We've already seen 2 algorithms, post merge sort and heap sort, that give us n log n. So, and this one is called quick sort, so it's supposed to be hopefully quicker. So it all comes down to how you choose the pivot. Right now, I'm not giving you any rules. So the worst case is that all of the choices go terribly bad, and then we lose everything, and we have n squared time. But what's the best case? What happens if I'm really lucky in choosing my pivot? Again, I don't know that this is the best case. Let's say this is my desirable case, because I don't want to go into proving that this is really the best possible case. My desirable case is when this pivot that I take is always the median, so that it really cuts the array into 2 equal parts, right? So my desirable case is to say that X is the median. If this happens, then what is my runtime? Again, my runtime on an instance of size n would be, well, I still need to do n-1 comparisons to find out which elements go to the left and which elements go to the right. But after I do the n-1 comparisons, I know that my left and right side, they both have the same number of elements and it's just half of the elements. So it would be plus 2t of n/2, right? Now, I don't know, like floor, maybe floor of n+1/2, I don't know. Something like this. Okay. I'm always very lazy about figuring out the plus ones and minus ones. Now, we've seen this before. This is basically very similar to the recurrence that we had for merge sort. It's basically O of n plus 2t of instances which have half the size of the current. So we know that the answer to this one is O n log n. So in other words, if I can somehow make sure that the pivot that I choose is always the best possible pivot in the sense that it's the median and it cuts the array into 2 equal parts, then I'll get the same runtime as in merge sort, the same asymptotic runtime as in merge sort. But I hope that in practice it would be still quicker because I'm not doing merge. And merge was an operation that I was not very happy with. It was taking time. Okay. So for now, let's just implement this. And then we'll come back and we talk about how to make sure that the pivot that we're choosing is the median or close to the median. Okay, so I'm going to just have qsort.cpp, let's say. You can see the code. Should I make it bigger or? Let's see. Actually, how do you make this bigger? Where are the options? Set default fonts. Oh, it made it smaller. 20. Hopefully this is good enough. Okay. Now the font looks terrible. Okay, let's do this again. Set default fonts. Let's do Ubuntu Mono. And let's do 25. Okay, this is hopefully better. So just like before, all I have is some number n that I read, and then I want to read n numbers, and then I just want to sort them. Okay, so let's say I have a maximum for my n, which is 10 to the power of 7, and I have my array A of size max. Okay, or actually, I can also do it with vectors. Who cares? Let's do it with vectors this time. So I just say I have a vector of integers called A, and for I from 1 to n, I read some number x, and I put it into this vector. And then let's say I want to just call qsort on A. Say A becomes qsort on A, and then for every element x in A, just like this. Okay, let's write our quicksort. Okay, so I have this array A, and I want to sort it. First, we do the base case. We say if the number of elements is less than or equal to 1, just return A. Okay. Now, the other case is that I have to pick some pivot element, and I don't know what element to pick here, so I'm just going to pick the first element for now. I'm just going to pick A0. Now, after I pick A0, I have to make my left and right arrays. Again, I'm doing this with vectors. This is very time consuming, but that's fine. And I just say for every y in A, if y is less than x, put it in the left side. Otherwise, put it in the right side. Okay. And then finally, I just take, let's say I sort both sides. So L becomes Q sort of L, R becomes Q sort of R. And oh, I forgot here to put X itself. So I don't want to just sort L and then add R to the end. I want to sort L and then add X because we have to remember our pivot, and then add R. Okay, so I'm just going to say add X to the end of L and add R to the end of L. I don't think this would work. I hope it does. If it doesn't, I have to actually code it, which is more painful. It doesn't. Yeah, so I'm just gonna say for everything in right, L dot push back. Okay. Opening or line 15. I'm doing something. Oh, sorry, this was supposed to be by. I always have typos. Okay. So hopefully this works. 5. No, it doesn't. So what did we do wrong here? I forgot to read the inputs. Very typical. Okay, 5, 1, 2, 3, 4, 5 numbers. And again, it's not working. Is this because of this? Let's see what happens if I just do the copying. 5, 2, 5, 4, 7, 3. No, that's not the thing. If the size is less than 1, return A. X is A0. I have a left and a right for every Y in A. If Y is less than X, put it in the left, otherwise put it in the right. Sort both of them. And then L dot pushback X for every I in R, L dot pushback I, return L. I don't know what's going wrong here. Okay, let's debug this. It doesn't even tell me where I'm getting the error. Awesome.
I think X is already on.
X is already, oh, right. Y is greater than X. I have to really start writing these codes in advance. Yeah, thanks. Now it's working. Great. And of course, it's very wasteful to use a vector here. It would be much better if you use an array. But this is an algorithms course. We only care about O. Okay. Now, what is the worst possible input that I can give to this code? So this is quicksort. And every time when I want to choose a pivot, I also element as my pivot. Okay. So actually, if I already give it an input which is sorted, let's say my array A is already sorted. Every time when I'm picking the first element, I'm really literally taking the smallest element. So this kind of sort is terrible when the array is sorted. And also if the array is reverse sorted, the exact same thing happens as well. So I don't want to do that. I don't want to have this kind of pivot. So the next idea that comes to mind is, let's choose the pivot randomly. Right? Let's just use a random number generator to pick my pivots. So what happens if I do that? So let's say instead of saying that I take A0, I take A rand modulo A dot size. Does this compile? Yes. Okay. So I'm just picking my pivot at random. Does this help? Now, again, it doesn't help in the worst case, because if I want to do a worst case analysis, I might just be really unlucky. And every time that I'm picking the pivot, even though I'm picking it randomly, I might end up taking the smallest element. And actually, of course, you know that generating random numbers in C++ is also not possible. So this is actually a deterministic sequence of numbers that the rand function is giving you. So I can always cook up some sort of input that gives you an n-squared runtime. But what if I assume that this is really random? And what if I want to look at the expected runtime? So I'm going to say T of n is going to be the expected runtime on an instance of size n. But that doesn't make sense because we have many different instances of size n. So I'm just going to say this is going to be the maximum over all possible instances. So the maximum over all possible inputs of size n of the expected runtime of my algorithm on that input. I'm going to take that one. And this expectation is basically over the random choices that my algorithm makes. If I define it like this, so this is going to be expected runtime analysis. And this is actually something that we will come back to towards the very end of this course when we talk about randomized algorithms. But all I want to show you is that I will get a very complicated recurrence relation now. So what is T of n? T of n is the expected runtime on the worst instance of size n. Now, what am I going to do with my instance? I'm just going to pick one of the elements at random as my pivot. And no matter which element I took as the pivot, I'm going to compare it with all the other elements. So again, if I just count the number of comparisons, I'm going to have n-1 comparisons. But then, depending on what the rank of my element was, depending on how many elements were smaller than my element, I'm going to have subarrays of different sizes. So I'm going to just create a sum here. And let's just do a casework. And my casework is that the element that I choose as the pivot is either going to be the first element, meaning the smallest element, or the second smallest, or the third smallest, all the way to n's. If the element that I chose is the I smallest element, well, first of all, the probability that I choose the I smallest element is just 1 over n, right? And then how much time am I going to spend? Actually, let me write it like this, 1 over n. Well, if I have the i's elements, then my left-hand side is going to have I-1 elements, and my right-hand side is going to have n-I elements, right? So T of I-1 plus T of n-I. So now this is my recurrence. And of course, I have a base case as well. Like if I have only 1 element or 0 elements, I don't have any comparisons. Now, if we have time towards the end of this session, I will come back to this, but generally we're going to have a whole session about solving recurrences. At this point, I just want you to trust me. This is going to be O of n log n. Okay. I promise I will prove it to you later. So this is just a promise. I'm writing it here so that you can hold me responsible for this later. Okay. So basically the story is that if I choose my pivot randomly, in expectation, I'm going to have n log n runtime. But that's not the same as having n log n runtime in the worst case. My worst case is still n squared. Okay, so the next question is, can I somehow make my worst case to be n log n? If I want my worst case to be n log n, I know one way of doing it. And one way of doing it is to just say that I always pick the median. If I have a way of always taking the median out and use the median as my pivot, I'm sure that my runtime would be n log n, even in the worst case. Now, how much time can I afford to spend on finding the median? I can basically do it in, I have to do it in linear time, in some sense, right? Because if I can somehow here find the median in linear time, and then I know that the rest of this is going to take linear time here, instead of n-1, I'm just going to have O(n), and then the answer to my recurrence is going to be the same. It's just n log n. So now based on this, my goal has changed. My goal is to find a median element in linear time. So this is our goal. Given an array A, with n elements, find the median of A in linear time. If I have a magic box that does this for me, then I can put that magic box into my previous algorithm. I always pick the median, and then everything works well, and I will have a quick sort that works in n log n time, even in the worst case. Okay. So let's talk about how we can find the median. But I'm going to actually extend this a little bit. So here's an extended version, or a generalized version. Let's say that I give you an array. So I give you an array A with n elements as before. But I also give you some number k between 1 and A. Okay. So I also give you some k. And this k is guaranteed to be between 1 and n. And I ask you to find the k smallest elements. Okay, so if I just plug k to be n plus 1 over 2, then I get my median element, right? So I'm just looking at an extended version where instead of asking for the median element, I'm giving you some rank, and I'm saying, give me the item with rank k. Okay. Now, surprisingly, we can actually do something which is very similar to quick sort. And we're going to call this one quick select. Now, quick select gets the array A, and it also gets this number k, and it is supposed to return the k smallest element. Now, the idea is exactly like before. It's just that I have my large array. I pick some element to pivot, and then I divide my array into two parts. So let's say I have this element x. I have now a left side and a right side. The left side are all the elements that are smaller than x. The right side are all the elements that are bigger than x. Okay. Now what? Now, again, the problem that we face is that, well, I want to find my case element. I might get lucky, and maybe on my left side, I have exactly k minus 1 elements, which means that my pivot, the element x that I took, was exactly the case element. So in that case, I would just return x, okay? So let me just write it here. I have quick select of A and K. Again, I start with picking a pivot, pick some x in A, and then I define my left and right sides exactly as before. So left is all the elements y that are smaller than x, and right is going to be the set of all elements y that are larger than x. Okay? Now, here's what I'm going to say. I'm going to say if the left side has a minus 1 elements, it means that the k smallest element is exactly x. So I just return X. So this is a case where I got really lucky. Now, otherwise, maybe I have K elements or more on the left-hand side. And remember that the elements on my left are my smallest elements. So if I have more than K elements in the left, I just have to find the K's elements in my left subarray. So I just call myself recursively. I just say do quick select, but do it on the left subarray and give me the case elements. Right? Otherwise, my case smallest element should be in my right subarray. So I can do the same thing. I can say otherwise, basically if the size of L is less than K minus 1, it means that my element is in the right subarray, so I have to do quick select on my right subarray. But here's the thing, all the elements that were in L are already smaller than everything in R. And X is also already smaller than everything in R. So I shouldn't find the case smallest element in I. I have to find actually the element which is at like K minus L minus first smallest, right? So these are the elements in L that I'm subtracting, and this one is just X itself, the pivot. Okay. So you see, this is very similar to quicksort, but there is a huge difference. And the difference is in the way that the recurrence works. So in quicksort, whenever I was doing quicksort on my entire array A, I had to call quicksort twice recursively. Once on the left-hand side, once on the right-hand side. But in quick select, even though I define my left and right in the same way, if you look here, I'm calling myself recursively only on one of the two, right? So I would expect that quick select is faster than quick sort. Okay, let's analyze this. Let's again do worst case analysis, and then let's see what happens here. Okay. So again, just trust me that the worst case is when we take a really bad pivot and our pivot is the smallest element or the largest element, right? So what happens in this bad case? So this is the bad case that I want to analyze. It's that I'm always getting unlucky and the pivot X is actually the smallest element in A. Okay. Now, if this happens, I can write a recurrence relation. What is T of n, the time that I'm spending on an instance of size n? I'm picking an element X, I'm unlucky, so this is the smallest element. So the left side is going to be empty, the right side is going to contain everything else other than X. So the size of my right side is n minus 1. And let's say my K was chosen such that I get unlucky and I have to do quick select on the right side. So basically I'm doing n minus 1 comparisons to create the left and right side. And then I have plus T of n minus 1. Okay. Yeah, so this is again n squared, right? Because you can just expand this. This is n minus 1 plus n minus 2 plus n minus 3, so on. So you can show that this is, and actually, of course, there is a T of 1, which is, let's say, 0. So T of n is going to be in theta of n squared. And of course, I always forget the base case. So I'm now putting something here so that I just remember it. So my base case is that if A has less than one element, then just return the first element. Okay. We can also do a sanity check, like if K is larger than the size of A, return some error. I don't really care about that. Now, again, this was a bad case. What is a good case? A good case, I'm no longer saying best case because I don't want to prove to you that it's really the best case, but a good case would be if every time that I'm picking X, I'm picking the median. I'm getting lucky and always picking the median. If that happens, so this is my good case, it's that X is the median of A every time that I'm picking it. Then again, I can write my recurrence relation. So T of 1 is 0, but T of n is going to be n minus 1 for the comparisons with all the other elements to create the left and right, plus, now I know that each of my two sides have half of my elements, but I'm going to call myself recursively only on one of the two sides. So T of n is n minus 1 plus T of n over 2, right? And this is great. I mean, even forget the minus 1. This is like n plus n over 2 plus n over 4 if you expand it. So this is at most 2n. It's On. Okay, again, we're going to talk in a different session about how to solve all the recurrence relations, but this one is pretty easy. If you expand it, you will see that it's in On. Okay. Now I can also do an average case, just like before. I can say when I'm picking this X, let's pick X randomly. But that kind of defeats the purpose, right? Because the whole point of having Q select was such that I could find the median, so that in my quick sort, I don't have to use randomization. If I could use randomization, I would just use randomization here in my quick sort, and I would be happy. I would say my expected runtime is n log n, O(n) log n, and I don't care about the worst case. So here, I can do something similar. I can say I pick this X randomly, but again, it defeats the purpose. So a better question is, how do you pick an X without using randomization so that you're sure this particular X divides your array into chunks that are large enough? Now, they don't have to necessarily be the same size. Being the same size is asking for too much. Even if I could make sure that when I pick this X, let's say 1/5 of the elements are in the left-hand side at least, and at least 1/5 are on the right-hand side. That would still be enough to give me a good runtime, right? So the question is not really how to pick the median. The question is how to find an element that gives us a good division. And this division doesn't have to be 50-50. Even if you give me a 90-10 division, I would be happy. Okay. So how do you do that? Again, this quick select thing is not going to work for us because, I mean, if you use randomization, it's going to work, but what's the point of that? Let's talk about a different algorithm. And this is the algorithm that we call median of medians. And this is my goal. Let's say that in the input, I have given you some array. I've given you an array A of size n. I want you to output a good pivot for me. So I want you to output some number x in A. Now I have to define what I mean by a good pivot. I want to say such that the number of elements that are smaller than x is not too small. And also the number of elements that are larger than x is not too small. So such that the set L, okay, let's do it like this. Let's say that I define L to, again, be all the elements in my array that are smaller than x. and I define R to be all the elements in my array that are bigger than X. And I'm asking you to output an X such that L is bigger than something and R is also bigger than something. Now, what should I put here? Ideally, I want to just say n over 2. Okay. Ideally, I want to just break my array into 2 equal parts, but that's too hard. So I'm going to do something much simpler. I'm going to say, let's do n over 100 for now. We might change this number to something better later on. But all I'm asking for is that you give me a pivot that is good enough with this definition. It breaks down my array into 2 sides. I'm saying keep at least 1% of the elements in each side. That's not asking for much, hopefully. Okay. Now, before moving forward, I just want to show you that even if we have this kind of pivots, our quicksort will run in n log n. Okay. Why is that? So let's just do a detour and go back to quicksort. So let's say I do quicksort with this kind of 1% pivot. What does this mean? This means that if I want to again write a recurrence relation for my worst case runtime, so T of n, it's now worst case. I'm going to again do n minus 1 comparisons, let's say On plus. Now I'm calling my quicksort on 2 different sides, right? And one side is going to have T of, let's say, some I, and the other side is going to be T of n minus I, minus 1. And what do I know? I know that I is at least n over 100. And I know that n minus I minus 1 is also at least n over 100. Okay. Now, this is not a formal analysis. I'm just trying to give you the intuition. We will come back and do a formal analysis afterwards. But now my worst case is not that my pivot is going to give me nothing on the left and everything on the right. My worst case is that it's going to give me 1% on the left and 99% on the right. Right? So my worst case would be something like this. On plus T of n over 100 plus T of 99n over 100. Okay. And even if you solve this, you will get an object. Why is that? Well, I can just create my recurrence tree, right? So I can create my recurrence tree saying that I start with an instance of size n. And at this instance of size n, I'm paying a cost of n. So I write my instance size in green and my cost in red. Okay. Now I'm dividing this instance into 2 instances, one of size n over 100, another one of size 99n over 100. Right. And then I'm going to keep doing this. I divide this one into 2 parts, one of size n over 10 to the power of 4, one of size 99 over 100 times n over 100, basically. And here I'm doing the same thing as well. One is going to have 1/100th of the size of the original one, and the other one is going to have 99%, let's say. And so on. Again, this is not a formal analysis. This is not a formal proof. I'm just trying to give you some idea. What is the height of this tree? Yeah, it's still log n. But log n in what base? Yeah, okay. So every time when I'm going down, just look at the maximum size that I can have at every level. So the maximum size I can have here is n. The maximum size I can have in my second level is 99% of n. And I can have 99% of 99% of L, and so on. So as I'm going down, at every level, my maximum instance size is getting multiplied by 99%. So my height can be at most log of n in base 100 over 99, right? But we know that when we're working with logs, the base doesn't matter, right? So even if the base is something like this, which is very close to 1, this is still O log n, because this logarithm is just a constant times log 2 of n. So even though every time I'm breaking down my instance into two instances that are not at all close to each other in size, at the end of the day, the height of this tree is going to be O log n. Okay. Now, again, the analysis goes like every level of the tree. Let's look at every level of the tree and let's see how much time I'm spending at every level, or how many comparisons I'm doing at every level. So at this level, I'm doing n. Here, I'm doing n over 100. Here, I'm doing 99n over 100. Generally, whenever I have an instance of size n, I'm paying the cost of n, right? So you can see that if I just sum everything up, again, at every level, I'm spending O(n) time. So I have log n levels. At every level, I'm spending O(n) time. Overall, I'm spending O(n) log n. Okay? This was very hand-wavy. We have to actually make it much more formal than this. But it gives you the intuition for why I can divide my array into two sides that are very much different. Like one side is 99 times the other side, but still I get n log n runtime. Okay. Now, to formalize this, which hopefully I will give it to you in one of the homeworks to do it, you have to look at this kind of tree, but instead of being sure that every time you're breaking it down into two parts, where you put 1% on one side and 99% on the other side, you cannot be sure how this works. You just know that you will have at least 1% on each side. But you can create a tree in the same way, and you can do the exact same analysis. You can still say that that tree has a height of O log n, because you can just look at the maximum instance size at every level. And then you can say that at every level of the tree, you're spending O(n) time. So overall, it's going to be n log n, even if it's not this case. Okay. Now that we know that, let's go back to our problem. How do I even do this? So all of this was assuming that a fairy gave me something that would find a nice pivot. But now I want to actually try to find it. So again, I have an array of size n. My goal is to find a nice pivot. So what do you suggest we do? And I cannot do quick select, even though I really love quick select. Quick select only works if it's randomized. If it's not randomized, it takes n squared time, and I don't like that. Okay, so here's the thing. My budget on the amount of time that I can spend is O(n). Okay. And by the way, I cannot really exceed this budget. Even if I want to do n log n, the problem becomes trivial, right? Because in n log n, I can just sort my array. I've already seen merge sort. I've already seen a heap sort. They both work in n log n. And so if I had a budget of n log n time, I could just sort my entire array and then just output the elements like that is at the median. But my budget is very limited. I can only spend linear time. I can only spend O(n) to find a good pivot. So here's the thing. What can you do in O(n)? you cannot sort an array of size n, but you can sort smaller arrays, right? Sorting an array of size, let's say k, takes k log k time. So as long as k log k is smaller than n, I can sort an array of size k. That's one of the things that I can do if I have O(n) time. So I cannot sort my entire array, but I can sort a small chunk of it. The other thing that I can do is that I can take my big array and I can divide it into really small. Let's say I divide it into chunks of size 5, and 5 is just my lucky number. So this is my algorithm. Divide A into chunks of size 5. We will later see that numbers other than 5 can also work, but 5 is a good number here. And then I can say sort every chunk. Now, why does this work? Why does this work in O(n)? Again, remember our budget is O. Because I'm only sorting arrays of size 5. Sorting an array of size 5, since the size of the array is constant, the sorting is also going to take constant time. So I'm going to spend O(1) to sort every array of size 5. But how many of them do I have? I have O(n) of them. I have n/5 of them. So this dividing of A into chunks and sorting every chunk, it's not going to exceed my budget. Okay. So let's say I've done this. So I have a bunch of chunks, and in each chunk, I have 5 elements. Okay. And oops, no, I just wanted to copy this. Okay. So this is, let's say, my second chunk, my third chunk, fourth chunk. And then because I want to have 8 chunks, I'm going to just copy this. Okay. And maybe the number of elements in my array is not a multiple of 5. So maybe in my last chunk, I have fewer elements. Okay. But now just imagine that each of these dots is one of the elements in my array. And every column is sorted. Okay. And let's say that it's sorted such that the largest element of every column is at the top and the smallest element is at the bottom. Now, I would just say, let's look at the median element in every column. Let's look at these. Okay. And let's find the median of these medians. Now, how do I find the median? Well, I'm just giving you an algorithm. So I can just use the same algorithm. So I just find the median of these guys. So find some x, which is basically the median of medians. That's where I get the name. And what I mean is that the median of medians of chunks. Let's say that I have sorted these so that the medians are also in order. So I know that this is smaller than this one and so on. So this is what I have. And then 1, 2, 3, 4, 5, 6, 7, 8. So the median would be, let's say, at index 4. So let's say I take this one. And I call this x. I say this is my pivot. Now, why is this x good? So let's look at the elements that are definitely smaller than x. What do I know? I know that x was the median among these medians. So half of the medians are smaller than x. But these were each the median of their own chunk. So if I take x, everything here is smaller than x. right? Okay, that's good. Well, I mean, of course, without x itself, so something like this. All these elements are smaller than x. Now, there are a bunch of other elements up here. So for example, this one, I don't know if that one is smaller than x or not. Because all I know is that it was larger than the median in its own chunk, and that median was smaller than x, but that doesn't tell me whether this element was smaller than x or not. So I don't know that. The elements that I'm sure are bigger than x. Again, it's just the mirror image, right? So it's this. All of these elements are definitely bigger than x. That's because, well, the ones who were medians, x was the median of medians, so half of them are bigger than x. And in each group, I had two elements that were larger than the median. So all of these are definitely larger than the median, which was larger than x, so they're larger than x. Okay, these are all greater than x. Okay. It kind of looks like we have like 1/4 on each side, but it's not actually 1/4. What is the exact proportion? So if I have n elements, what is the number of elements that I'm sure are smaller than x? Okay, let's just do the math here. What is the number of chunks that I have? It's n over 5. Right? Now, so what are the number of chunks that start from the smallest one and go all the way to the median? It's going to be n over 5 over 2, something like this, right? So this is the number of chunks from here all the way to here. And then in each of these chunks, I have 3 elements that are smaller than x, except for the last one in which I have only 2 elements. So this is times 3 minus 1, right? So I am sure that I will have at least these many elements that are smaller than x. Okay, at least these many elements smaller than x. Sorry, these many elements smaller than x. Now, what is this? This is like, let's get rid of the ceiling. Let's just do this and write 3n over 10 minus 1, right? So I have at least this many elements that are smaller than x, almost 30%. How many elements do I have that are larger than x? I can do something similar, right? I can just do the same analysis. I can say the number of chunks starting from the chunk that contains x and going right is at least n over 5 over 2. And in each of these chunks, I have 3 elements that are larger than x, except for this one, where I have 2, and the last one, where I might have nothing, right? So instead of minus 1, I just have to do minus 4. But who cares? If n is really large, there are at least 3n over 10 minus 4. I might be wrong in these numbers. I'm really bad at calculating things. There are at least these many elements larger than x. Okay. So x is definitely a good pivot. Right? If I have a set of n elements, and if I find an x like this, it's going to give me a good division on both sides. But the really important thing is that I did this by asking for the median of these medians. So I should actually have a recursive algorithm to find that median. So I cannot just do something like this. I cannot just say, okay, output a good X. Instead, I have to also have an algorithm for selecting a median, right? And then I have to do this recursively. So I'm going to do this thing. Let's say I just call it select. And what select does is that it takes some array A and some index K. It has to return the K's smallest element. Okay. And then I'm going to use this procedure here to find basically my X. So I'm going to start first by finding a good pivot. Okay. So I break A into chunks of size 5. Okay. So I say break A into, let's call it chunks A1, A2 to AN over 5 of size 5. Then I'm going to have another array. Let's call this array M. And basically, I'm going to say let Mi be the median of the ith chunk. Okay. And this is for every I, for I from 1 to N over 5. Okay. So I calculated all the medians. And now I want to find the median of medians. So now I have to do a recursive call. I have to say my X becomes the select in this array M of the median element. What is the median element? It's the element at index M plus 1 over 2, size of M plus 1 over 2. Okay. Now I have a really good pivot. And now I can use this pivot to continue my selection algorithm, just like what I was doing in quick select. So now that I have my pivot, let's compute the left and right side arrays based on this pivot. I don't know what happened to my D there. Okay. So I'm just going to say L becomes every element in my original array that is smaller than X, and R becomes every element in my original array that is bigger than X. Okay. Now remember, again, my goal was to just find the K's smallest element. So I have now found a good pivot, and I have divided my array into 2 parts. But now I have to do the same thing that I did before. I have to say, if I got lucky and my pivot is exactly the K's element, return the pivot. Otherwise, if the left side has at least K elements, return the K's element in the left side. Otherwise, take it from the right side. So I'm just going to copy this and put it here. Okay, it's just that instead of quick select, now we're calling it select. So I'm going to just say select. The Q. It's easier to remove it like this. Okay. So this is now my algorithm. So this is basically the same as quick select. The only difference is in the way that I'm finding my pivot. And in order to find my pivot, very simply, I'm first breaking my array into chunks of size 5. Then for every chunk, I'm finding the median. And then I'm selecting the median of these medians. Now, okay, first of all, breaking it into chunks of size 5, that's going to take linear time. And then in each chunk, I have only 5 elements. I just want the median of 5 elements. That's also constant time, but I do it linearly many times. I do it for n over 5 chunks. So all of this part, the part that is selecting something is taking O of n, sorry, before the recursive call. This part is taking O of n. And then, of course, I have this recursive call, right? I'm calling select again. And then I have this part, but this part is again taking O of n because I'm just comparing all the elements in my array with my pivots, right? And then again, I have my recursive calls. But whatever I'm doing outside of my recursive calls, it's 2 parts that are taking O of n, so it's O of n overall. But now I want to analyze the total runtime. So what is the runtime of my algorithm? Do I make this fit? Okay, yeah. So let's do the runtime analysis. And this is worst case. Okay. So I don't have any randomization in this algorithm. This algorithm was 100% deterministic. And oh, by the way, there is a base case that I'm forgetting here, as always. So remember to write your base case. Now, okay. What is my runtime analysis? If I have an array of size n, what am I doing? I said that I spent O(n) time here and here. So I have O(n) for that. But I also have a recursive call here to select the median of medians. But this is a recursive call that is being called on an array of size 1/5 of the size of the original array. So this is T of n over 5. Ceiling of n over 5, right? And then I create my left side and my right side. And I know that I'm going to call myself recursively over at most one of them, right? So I either call select recursively on the left side or I call select recursively on the right side. But the question is, what is the size of this array that I recursively call select on? What can this array have? What is the largest possible size that this array can have? Let me ask you that. So you see, I know that in my L, I have at least 3n over 10 minus 1 element. I know that in my R, I have at least 3n over 10 minus 4 elements. But I'm asking how many elements at most. I'm not asking at least. So if the left-hand side has to have 30% of the elements at least, then that means that the right-hand side can have at most 70% of the elements. And vice versa. The left-hand side can also have at most 70% of the elements, plus 4, right? So what I know is that when I'm doing this recursive call at this point, let's call this star. For this star, the time that I'm spending is at most 7n over 10, T of 7n over 10 plus 4, right? Okay. Now, why is this good? Why is this a good recurrent? Or another way of asking this question is, why did I choose chunks of size 5? Why didn't I choose chunks of size 3 or 7 or some other number? Look, this recurrence is linear because imagine that T of n takes linear time, right? Then this one would take n over 5 time intuitively, and this one would take 7n over 10 time. But this, like n over 5 is 20%. This is 70%, so overall it's 90%. Right? So it's less than n intuitively. Now you can, again, I do these rough calculations all the time, but we will talk about how to solve recurrences exactly later on. But you can do basically an induction here. And oh, by the way, my base case is that T of n is O of 1. Right, so T of n is going to be O of 1 if n is less than whatever 1000. Right, so that's my base case. I don't care about my runtime if my array is small. And if my array is not small, I'm basically starting with an array of size n, but I'm recursively calling myself over two arrays, one of size n over 5 and one of size 7n over 10 plus 4. I don't care about the plus 4 that much, right? Now, the important point is that the sum of the sizes of these two subarrays is smaller than the size of my original array. And it's also smaller by some constant factor. So again, I can draw this tree. Where's my tree? Oh, it's in the next slide. Oh, you're going to get these slides in random order now. So I can draw this same tree again, right? And let me actually do it. So this is what I have. Okay, first of all, I want to get rid of all of these things. So I can say T of n is On, or it's less than or equal to On plus this n over 5, it's 20% of n. Let's make it 21%, right? I'm just over approximating. So 21% of n plus T of, and let's make this one 71% as well. And that helps me get rid of the 4 because my n is larger than 1000, right? So 71% of n. This is what I have. So if I draw the tree, I have an instance of size n now, and I'm dividing it into two instances. One has size 21% of n. The other one has size 71% of n. And then I'm doing the same thing again and again, right? So this one is going to have 21% to the power of 2 times n. This one is like 21 times 71 over 10 to the power of 4 times n, and so on. Now, what is the extra cost that I'm paying? It's On when my input size is n. So here I'm paying a cost of n at this level. At this level, actually, I'm paying a cost of at most 92n. Sorry, 92% of n. I forgot that. Yeah. And then in the next level, I'm going to pay a cost that is 92% to the power of 2 times n, and so on. Anyway, all of these costs are less than n. And I can say that the height of my tree is at most log n, because of course, every time I'm multiplying by 71%. So it's going to take at most n log n time. But n log n is bad. I want to say it takes On time, right? Now, the thing that you have to realize here is that this is actually a geometric series, right? So at the top level, I'm having a cost of n. In the next level, my total cost is at most 92% of n. In the next level, my total cost is 92% of the previous level, and so on. And I'm just summing all of these up. So my total cost is basically n plus 92% of n plus 92% to the power of 2 times n, so on. And I don't care how long it goes. Let's just sum this up until infinity, right? I mean, this is a finite tree, but I'm going to do my sum forever because I'm just over approximating, right? And this is a geometric series, and I don't remember the formula for geometric series, so I'm going to give it to Wolfram alpha. The sum of all these numbers, it's just the sum of a geometric series, which is a constant. And we're multiplying it by n, so it's going to be at most that constant times n, which is in O of n. Okay, so finally, we have an algorithm for select, which works in linear time, right? And it works in linear time, but by calling itself recursively to find this median of medians, which is going to be a good pivot. Now I can use this select inside my quicksort, right? So when I'm doing quicksort, every time when I want to pick my pivot, instead of just picking it, I say use the select. So actually, instead of doing this, I say let X be the median. So I'm going to select from A the element at index size of A plus 1/2, the median. So remember, my select works in linear time. So every time I'm finding the median in linear time, and in my quicksort, I'm using the median to break my array into 2 equal parts. And then I sort each of these parts separately, right? So now my recurrence relation is basically this one, except that instead of n-1, I'm going to have On, right? So I'm spending On for 2 things. First, for finding the median of medians, for finding the good pivots, or actually, no, sorry, I got confused. I'm going to remove that part. So I'm using On for this select, which is giving me literally the median. And then I'm also spending On to find the left side and the right side, right? So the overall overhead here is On. And then I'm just calling quicksort on the left-hand side and the right-hand side, which gives me 2t of n/2. And this is the same recurrence relation as in merge sort. And again, just draw the tree. This is n log n. Okay. So finally, as we get to the end of this session, we have a quicksort algorithm that is not randomized and has a worst case runtime of O(n) log n. Okay. And we don't need to do merging. We did all of this session so that we don't have to do merging. And yeah, here's the kicker. In practice, when you're implementing it, randomized quicksort works much better than this. So all of this was to just avoid the worst case scenario where you have n² runtime. But if you're actually implementing this for a real world use case, just implement randomized quicksort, and it works much faster than all of these. But in theory, this is better. Okay, I'll see you tomorrow.